Thank you everyone for coming. Today we're very happy to have Edoardo Vitagliano from UCLA giving us a talk on axion production mechanisms from string networks that produce gravitational waves. Eduardo is visiting for a few weeks. He'll be here for another 2 weeks, I believe. So he has an office somewhere and will also visit.
Every day is different, so you have to hang it out.
Okay, take it away, Eduardo.
Okay, thank you. So thank you for the introduction, and it's a pleasure to be here again after 2 years ago. It was an important visit my first time because it was the beginning of COVID. Now I'm back, and today I would like to discuss with you about something I've been working on during the last year and a half, I guess, at this point, which is the possibility of dark matter being made up of Axion-like particles. This doesn't sound that new. What is new is that actually, no matter how feeble the interactions of these Axion-like particles are with the ordinary standard building block of matter, so basically some of the particles, we might still be able to indirectly detect a signal coming from their production. Basically, as you might expect from the title, this signal will be in gravitational waves. So before diving into the talk, I would like to start with the prologue. And I'm pretty sure that senior people in this room have seen this slide really too many times, but still, it still makes sense to remind ourselves how successful the Summer model has been in the last, I don't know, 40 years or so, in describing a plethora of physical phenomena. On the other hand, we do know already that there are many known unknowns in particle physics. We know that there is a mystery of how we have matter rather than antimatter in the universe. We have the horizon problem, so this means that we might discover something related to inflation someday. And we do know that the universe is expanding at a rate which is unexpected, so we do know that there is dark energy. As a theoretical astroparticle physicist, I'm focusing on dark matter searches at the moment. And so the question I'm trying to answer is, what is dark matter? Well, we have a bunch of proofs that dark matter exists. And you might see that I'm talking about the coma cluster, cosmic microwave background data, the bullet cluster. In general, there is something in common. Like all these proofs, they have something in common. They are all gravitational in nature. So basically, even if we hope that dark matter have some reasonable interaction with some of the particles so that we might eventually detect what it is and discover its nature, it might also be possible that we live in a nightmare scenario and actually dark matter interacts so feebly with the Standard Model that we might never be able to detect it, right? So let's suppose that we live in this nightmare scenario, and I want to make the nightmare scenario a bit less nightmarish during this talk. Okay. So the talk is structured as follows. In the first part of the talk, I will briefly mention how, what's the status of gravitational wave astronomy today, in 2021, and explain how dark matter production might be related to the production of gravitational waves in the early universe. Then in the second part of the talk, I will talk mostly about particle physics, and I will show how the QCD axion has a certain peculiar cosmology that some of you might already be familiar with, and how these can be generalized to axion-like particle cosmology. And finally, I will build a bridge in between the particle physics side of the story, the observational side in terms of gravitational wave side of the story, and we'll see how eventually we might produce 100% of dark matter in form of axion-like particles and detect a signal associated with the production of these axion-like particles. So we can start with the first part. And as much as most of us don't accept it, Wikipedia is a great starting point for learning about anything. And from the page talking about multi-messenger astronomy, I can directly read from the slide that multi-messenger astronomy is based on coordinated observation, interpretation of different messenger signals. and it's based on electromagnetic radiation, radiation waves, neutrinos, and cosmic rays. Now, it's a well-known thing that we can search for dark matter using at least 3 of these messengers. In terms of photons, we have been looking forever for KV lines, for well, it depends on what's your favorite dark matter candidate. Similarly, for neutrinos, for example, you might imagine a PV dark matter, a Wimpzilla decaying to neutrinos, and you might observe these neutrinos, for example, at ice cube. And similarly, cosmic rays have been used to constrain the features of a plausible dark matter candidate. Gravitational waves at some level have been kind of overlooked, but it's pretty clear that we're not in the 17th century anymore. We don't have just electromagnetic radiation to explore the universe, both in terms of astrophysics and in terms of particle physics. So I would like to stress that the gravitational waves are a very good candidate as a probe for dark matter, depending on the dark matter candidate. So in 2021, the status of gravitational wave astronomy is more or less the following. So you might be for sure familiar with the fact that people are looking for gravitational waves in LIGO. And the idea basically is that depending on the frequency of gravitational waves that you want to detect, you have to rely on different experimental schemes, right? So, for example, if you are looking for astrophysically generated signals of gravitational waves, you will use some kind of Fabry-Perot interferometers, as you see here. If you are looking for something at lower frequencies, let's say 10 to the minus 9 hertz, then you have to rely on something else. In this case, on pulsar timing, because basically pulsars are very precise clocks. So it means that I can look for the time of light from pulsars. And it means that experiments like the European Pulsar Timing Array and Squared Kilometer Array can look for gravitational wave signals. But what happens if I consider gravitational waves with the smaller frequency, which usually, just like the high frequency ones, are sometimes overlooked? Well, it depends. So below 10 to the minus 9 hertz, you have to rely on something else because you don't have pulsar. You cannot rely on pulsars. So first of all, you can rely on astrometry. And this is how you obtain bounds, for example, from the very long baseline array. So the idea is that gravitational waves cause an apparent distortion of the position of background sources. So they look like it's moving. They are moving because the gravitational waves is passing in between the sources and us. And so as a result, you can put bounds on the amplitude of gravitational waves in this way. Other two kinds of bounds can be obtained either from an effective, because gravitational waves, it's obviously radiation, so it contributes to the effective number of neutrinos. And you can rely on the fact that gravitational waves can affect both temperature and polarization on isotopes in the same way. And this is how you obtain bounds, for example, from this, which is based on Planck. And this is the projection coming from a futuristic CMB experiment. But like for the moment, what we need to know is just that we can put bounds on gravitational waves with frequencies below 10 to the minus 14 hertz, let's say, with CMB probes.
The future reach versus now is a factor of 1,000.
Yes, it's like a yes, and that's because basically, in principle, we might improve by a lot the bounds using B modes rather than temperature anisotropes, because B modes are still limited by the experiment, whereas the temperature anisotropes we cannot improve that by much because at a certain point,
Even with like foregrounds and stuff.
yeah, exactly. At a certain point, it's gonna be
For B modes with foregrounds, they can go 1,000.
well. Again, this is very optimistic because I can show you what are the assumptions behind this line, but like they are very optimistic. Just focus on this and just imagine that you can go down from here, because like what I'm gonna show in the end is that this is already enough to put some bounds on the parameter space.
So the red line and the yellow line is just current bounds from Planck, just different.
Yes,
different
these ones
effects,
are current bounds.
different effects within Planck.
Yeah, one is an effective and one is anisotropes.
Sorry, I don't understand. 10 to the minus 16 hertz,
Yes.
right? So that's a time of a billion years.
10 to minus 16 hertz corresponds to matter radiation quality here. Because you have to imagine, like this corresponds to.
No, my question is really trivial. Isn't 10 to the minus 16 hertz a time of 10 to the 16 seconds?
Yes.
10 to the 16 seconds is a billion years, right?
Yes.
So a wave that has a period of a billion year, how can you detect it's a wave? I mean,
I know, but this is not direct detection. Like this is an effect that is on CMB. So you have to account for the redshift.
so
Because
the
when it was detected, it was at the 1000.
Yeah, exactly.
Okay, you take out 1,000, but still, are you detecting waves or are you detecting something else?
Yeah, actually, I would say it is direct detection, right? Because CB polarization, it's the same effect, like of that.
I mean, you are not waiting that the wave passes. You're just looking in the sky.
Yes,
Well, you see quadrupole, which is induced on the primordial plasma, right? So in that sense, it's the same direct detection, just using primordial plasma as a detector. But it's the same direct detection is with LISA, just using that different quadrupole.
Yeah, but like again, but it's not a public it's not a public interferometer.
We don't need to build it.
Yeah, sure.
Otherwise, it's the same idea.
Yeah. Okay. So let's have more. So basically, the idea is that if there are large objects near the universe that are moving around, they might produce gravitational waves and eventually even increase at low frequency. And at this point, the question that we might ask ourselves is, what are these large objects we are talking about? And the answer is topological effects. So if there are students in the audience, you might be familiar with topological effects coming in the context of condensed matter physics. So basically, if you imagine a ferromagnet and you go to low temperature and you reach the Curie temperature, eventually the spins of electrons in your system will need to choose a direction, and there will be a topological objects dividing the different patches of your ferromagnet in spin up and spin down, and that's a domain wall. And in cosmology, something similar happens, and it was described by Zeldovich in 1974, and in particular Kibble in 1976, who described how the early universe, as you cool down the universe during expansion, depending on the pattern of the breaking of your symmetry, you might form topological defects. And again, depending on the pattern, you might form monopole strings, domain walls, or textures, and they have different dimensions. Obviously, so monopoles are 0-dimensional, strings are 1-dimensional, domain walls are 2-dimensional, and then textures, I won't say what's dimensional. And during the talk, we will focus on strings and domain walls because they are associated with the Axionlike particle production.
What are textures?
Huh?
What are textures?
Textures is it's another kind of topological effects that arises in the symmetry plane of more complicated symmetries, and they don't really have a dimension. That's problem with textures.
It's like living inside the skew inside the solid.
So cosmic strings, they're simple. So basically, they arise every time you have the breaking of an axial symmetry, like O something, U1, for example, and they come simply from the fact that the 1 in number is different from 0. So in layman terms, it means that you start from a universe which is symmetric, then the temperature goes down, and different patches of the universe fall into different vapor. So it means that if you consider each patch falling into a different vapor, in the middle there would be a configuration which is a cosmic string. So the evolution of a string network can be described in simple way because after a transient, eventually the string network will reach a scaling regime in which you have order 1 string per Hubble volume. And this happens because you have to account both for the string reconnection, so strings intersect each other, they cut each other and so forth. And in the meanwhile, you also have expansion. So these two effects counterbalance each other, and eventually you have like 1 long string per Hubble volume. Similarly, domain walls are produced when you have the breaking of a discrete symmetry, for example, Zn. And this is the example of the ferromagnet I was doing earlier. You again start from a symmetric universe, then the temperature goes down, and eventually a patch in the universe could either fall into the left vacuum or the right vacuum, and in the middle there would be a domain wall. Again, just like strings, domain walls reach a scaling solution, whose energy density evolves like sigma over T. Now, the problem of this scaling solution for the walls is that walls are problematic because a wall-dominated universe undergoes a power law inflation, which is a misnomer because it's not an exponential growth in the Hubble function. It just goes like scale factor goes like T squared, which is too fast. So it means that you have to get rid of these walls. If your theory produces domain walls, you have to get rid of them in some way. Now, there are different ways of getting rid of walls. First of all, of course, you might resort to inflation, to a low scale inflation. So, for example, your theory is broken, you produce domain walls, but inflation is at a lower scale, so you just wash them away, and you're left with no domain walls. Another alternative might be it's the Shapi-Lazaridis mechanism. I won't go into detail with this, but depending on the pattern of the symmetry breaking, you might avoid the formation of domain wall altogether. But in general, you have to take care of what happens with walls. And a solution to the problem of domain walls, if we don't want to resort to inflation, because perhaps inflation is at a high scale, is perhaps given by the existence of a bias between the two vacua. So basically, there is an additional breaking between the different vacua. In this case, Z2, you have two different vacua, left and right, and there is a bias, an energy difference between the left vacuum and the right vacuum. So eventually, the whole universe will end up just in one vacuum, because this energy difference causes the acceleration of domain walls. And so just like combustion, this energy difference is converted to kinetic energy of walls that eventually annihilate. And so you're left with no walls.
Could you remind what is the bound of the largest tension which is allowed if there is really a network?
This depends. So with in the case of only walls, it's around it's a Zeldovich bound, so it's like in the order MeV. But like in the case we're going to describe, it's a different situation because my situation will deal with walls bounded by strings, which is slightly different because for axion-like particles, just like for axions, you have the formation of walls after the formation of strings. So you have the initial U1 symmetry breaking, you have the formation of strings, and then at a much smaller temperature, which corresponds to the temperature at which the quantum wavelength of the axion enters the horizon, then you start forming the walls. And depending on the so-called number of domain walls, usually people call it just n dw, number of domain walls. If n is equal to 1, which means that you have just have one real vacuum, then you form only strings. And when you form walls, actually they look like ribbon, and they are unstable. So they quickly decay to axions, and you cannot have any signal in gravitational waves coming from ribbons. Whereas if you have n larger than 1, which means that you have an n larger than 1 number of vacua along the orbit of minima, so you have different minima, then in that case, the same wall network is stable, and you need to get rid of it, just like in the case of walls. But the energy scale, which the tension will be different. Like the bounds of tension will not apply in this case. What?
So, what would be the tension of the strings or the tension of the domain walls that you are considering? What is the scale that is relevant here?
So I'm gonna reach it like later in the talk, but this depends. So the scale for the string formation can be up to 10 to 14 GeV. And all the way down to GeV. Whereas the tension for like the walls get formed much later, as we'll see. Like they are formed basically, they can be formed at temperature around 100 electron volts, for example.
And in these models, you take that the tension is constant or it evolves with the.
So okay, the tension of the strings it will be irrelevant because this. Can we go back to that later? Because otherwise, I have to spoil my own talk. So
Can I ask a question?
Yeah, sure
about that? So what, for n equals 1, why does that not produce gravitational waves?
because these are unstable. So basically, they emit axions very fast, you have the strings going against each other in a small amount of time, so in a Hubble time. So basically, this thing dissolve as soon as you form the walls, which happen when the common wavelength of the axion enters the horizon. Whereas if you have n larger than 1, this is stable, and so you need the bias to make it disappear. Whereas in this case, you don't need bias. So the only gravitational wave signal in this case is coming actually from the strings.
Just because you have more time, there is some gravitational wave.
But the signal is irrelevant, so it's so small. So actually, the only signal that you can see in this case is coming from the strings, and this is coming, and you can see it's observable, like in terms of like pragmatically observable, only if the symmetry breaking scale of the U1 symmetry breaking scale is around 10 to the 14 GeV or more. So it's a very limited part of the parameter space. There was this paper by Borghetto et al. Doing precisely this. So particle physics models. To discuss axion-like particle cosmology, I will briefly describe the QCD axion cosmology, and we'll see what are the differences with the axion-like particle case. So there are probably as many physicists as there are possible description of the strong CP problem. I will pick one, and you get on. Okay, so here we have an honestly out of scale description of the neutron, which can be seen in a kind of Beck model inspired picture as a certain distribution of plus and minus charges and a certain spin. Now this will be described by an electric dipole moment and a magnetic dipole moment. So this is particularly for the students. If I apply a parity transformation in layman terms, it means that I'm sending x to minus x, y to minus y, and z to minus z. And eventually it means that given that the magnetic dipole moment is an axial vector, it will not change its direction, whereas the electron dipole moment will. So it means that the presence of an electric dipole moment violates spin, because I can distinguish these two states, right? It's a nice long immense, but what if I apply a time reversal, which again in layman terms, I'm sorry to the formal people, but let's suppose that you run the movie backwards. It means that the particle spins the other direction. The magnetic dipole moment proportional to the spin will point downwards. And so again, you can distinguish these two states. It means that the electric dipole moment violates time reversal. If we assume a CPT theory, because we do, it means that we are violating CP. So the presence of a neutron electric dipole moment violates CP. I go to my experimentalist friend and I ask them to measure the electric dipole moment of the neutron, and they tell me that it's very, very small. Now, in particle physics, if we have a small number, we have to explain why it's small, and perhaps this is because it's not allowed on symmetry, on a symmetry level. Then I go to my theorist friend, and I ask them, why is the electric dipole moment so small? And they tell me, look, if I write down the QCD Lagrangian like in a dumbed down version, I have a certain part for quarks. Notice that there is a real mass and Yugawa phases. Then there is the kinetic term for gluons, and then there is this term, which is GG dual, and that's the famous or infamous, depending on your point of view, term in the QCD Lagrangian, which is CP violating. Now, this term, if we remove the phases in the Yukawa matrices, becomes proportional to theta minus the argument of the determinant of the quark mass, matrix. And this is what we call theta bar, which related to the electric dipole moment of the neutron means that theta bar must be smaller than 10 to minus 11. Now you see that the number is small. There are some people that like the anthropic principle. If we say that anthropic principle might be a valid explanation for particle physics phenomena, we must also admit that actually such a small theta bar is not explained in terms of anthropic principle, because if it were larger, the universe would kind of look similar to the universe we live in. So actually, it's not ruling out our existence. So we have to answer the question, why is theta bar so small? And the solution people came up with in the 70s was that there is an additional symmetry, a global symmetry, the so-called Pacheco symmetry, in which I get rid of GG dual term by introducing again this additional symmetry, which rotates away the theta bar term. Now, what is important is that the Pechenwin symmetry explain the existence of a pseudo-Wilson boson, which is the axion, which rotates the angle away, and so we solve the strong CP problem. But for us, what is important is that the same rotation gives also a mass to the axion, which in the case in which I assume just 2 words, this is actually realistic, but let's suppose. The axion mass has 2 different features. One is that in this case, like U bar U, it's called bilinear, so there is a temperature dependence, and that's different from a mass coming from an explicit breaking, for example. So there is a temperature dependence which is non-trivial and comes from instant effect. And the other thing is that the axion mass scale as the inversely proportional to the Pechenwin symmetry breaking scale. Now, this means that if you give enough time to your universe, it allows it to CP invariant phase, right? But we'll see that for action-like particles, there are some differences which are crucial. For the QCD axion cosmology, I will go fast through it. But what is important is that I can write the production of axion of QCD axion dark matter is very simple. Let's suppose for the time being that we are in the pre-inflationary scenario. So it means that we break the Pechenwin symmetry breaking, the Pechenwin symmetry, and then we have inflation later. So it means that the only contribution to the axion population is coming from the misalignment mechanism, which is very simple. I just write down the Klein-Gordon equation for the axion, and I wait long enough so that the damped harmonic oscillator dies off, and we can forget about the ALP term. And eventually, what I have is a certain energy density stored in the axion field in the form of dark matter, because it's cool. That's why it's cool. And this means that the axion can be a dark matter candidate. These are the 2 things. The axion, the QCD axion solves the strong CP problem, and it's a good dark matter candidate. However, let's suppose that we want to generalize it to axion-like particles. There will be several differences, because in the case of the axion, of the QCD axion, if we are in the post-inflationary scenario, which means that inflation happens before the Pechenwin symmetry breaking, then the result is that while in the pre-inflationary scenario, the whole universe will fall into a fixed misalignment angle, in the case of the post-inflationary scenario, different patches of the universe will fall into different misalignment angles, and there will be the formation of topological defects. Now, this is particularly interesting because while we cannot predict the axion mass in this case, because the misalignment angle will be random in between 0 and 2 pi, in this case, you have to average over all the possible angles. So in principle, you have 2 conditions, which is dark matter abundance and solving the strong CP problem, which means that you can predict the axion mass. Now, the difficulty in predicting the axion mass is that actually it involves the calculation of axions produced from topological defects, and people disagree about how many axions you have produced by get produced by topological defects. In general, anyway, people are focusing on detecting axions, just the axions of this mass, and examples of experiments looking for axions in this mass regime are made max of the plasma haloscopes that we produced a few years ago. Now, the main difference of the axion-like particle with the QCD axion is that, first of all, it's independent from T because it doesn't need to depend on the work bilinear. And the second thing is that the axion-like particle mass, that from now on I will call just axion, is not that it's not inversely proportional to the U1 symmetry breaking scale. It can be whatever. So,
Sorry, back
yes.
a sec. You said people disagree because they know it's
on
hard.
the value of the one.
No, sorry, on how many axions you make in the string case.
Well,
Like
yes. So
how much is the range now? Like it's
so it depends. There are group claiming that it's 25 microelectron volt, group claiming that it's 1 order of magnitude larger. And the reason is that the production of axion of QCD axion from strings depends on the tension of the string. And the tension of the string might or might not have logarithmic correction, which goes like logarithm of time. Now, this means that if there is such a correction, the contribution coming from strings is even like 2 orders of magnitude larger than one coming from the misalignment angle. On the other hand, there are people claiming that no, actually there is no logarithmic enhancement, so it's double counting, and you should only account for misalignment angle produced actions. That there was a paper by Michael Dine and friends like a few months ago now, and they were claiming that actually there is like the description of strings is not correct, and actually there is no surplus of axions coming from strings. So that's why there is this.
Giovanni works on this too, right?
What's it again?
Giovanni Villadoro.
No, they think so. They had Villadoro, the group of Villadoro, Gorghetto. They had several papers, and they showed that actually this depends on how you extrapolate your simulation, because actually you simulate the very beginning of your network, and extrapolating at later time, you might either have a lot of axions or not, depending on the momentum distribution of the axion that you produce, because it depends on how much energy, on what kind of energy you pump the string energy into. So if it's pumped into kinetic energy for axions, you just have a bunch of high moment axions. Whereas if they are produced non-relativistic or with low momentum, then you have a surplus of axions coming from string decay.
So they get a range, but Dine disagrees with their range, or
Dine
or
says
Dine's
that
within
actually,
their range?
Dine, that's so I have to read much more carefully their paper, but from what I understand, they disagree on the fact that the string contribution matters at all. So actually, you might predict the volume of the axial mass by simply averaging over the angles and using a misalignment angle. That's basically their claim in the end, because they say, okay, look, this logarithmic enhancement is not there, so you can forget about the string contribution. I will describe it later as well. So for what concerns Axion-like particles, my definition is very, very general. Axion-like particles are pseudo-number-Wilson bosons, even if nowadays everything is an Axion-like particle. They correspond to the spontaneous breaking of a symmetry time scale P, which is like in the case of the QCD axion, patching symmetry breaking. And whose mass is generated by an additional breaking at the smaller scale, small b, that you might see as lambda QCD in the case of QCD axion, which, yes?
So I have one question. So how do you make sure that the action produced from the cosmological defects is not dominated by the action produced from the misalignment effect?
Again, in the case of, as I was telling Josh earlier, in the case of strings, you have to simulate your string network. In the case of walls, you will see that it dominates by a lot, so you don't have to care about it. At least in what I will describe, there is a simple analytical argument to show that the production coming from walls is by far dominating if the bias is small enough. So the difference between the different vacua is small enough so that the walls annihilate very late. So it means that the axion population coming from walls do not get redshifted. I will get to it later. So example for Axion-like particles include Majorons or whatever, like Axion-like particles might arise in different theory-inspired model, but a description for the Axion-like particle Lagrangian is very, very simple. You just need the term which gives non-Wilson bosons to begin with. Then you need the mass generation, because otherwise it cannot be dark matter, obviously. And then you need the bias if n is larger than 1, because you need to get rid of the walls that get produced because of this term. So as the temperature goes down, each term becomes important in your cosmological history. So when the temperature is ordered big B, you have the production of string, you have the formation of strings, and these strings can emit axions while they oscillate and so forth. And they also can produce gravitational wave, but the signal is small. Then when the Compton wavelength of the Axion-like particle enters the horizon, you have the formation of walls and the misalignment mechanism starts. And eventually, given that the bias is small, walls annihilate late, and you have the additional production of Axion-like particles and gravitational waves from the annihilation of walls. Now, that's more or less what I described, but like I will give further details. So, as I was saying, when T is ordered B, you form strings, which corresponds to the breaking of the U1 symmetry. The string network, which is a scaling regime after the transient, as I said in the beginning, and the energy density goes like Xi mu over T squared. Mu is the tension of the string, which has logarithmic correction, as I mentioned, and Xi is an order one number coming from simulations corresponding to how many strings you have per Hubble volume. And the tension I was describing previously scales like the logarithm of T and you see that there are people claiming that this correction is not there. Basically, this thing corresponds to the tension of a of a gauge string, whereas this is what people claim to be a correction due to the fact that you have Goldstone bosons. But it's not gonna be relevant for our predictions. The second term, as I was saying, becomes important when the quantum wavelength enters the horizon, and this means that this happens at a smaller scale, much smaller scale than this. And it identifies a temperature of wall annihilation and when its alignment mechanism kicks in. We can also write down the tension associated to these walls attached to string as a F sigma, which is a model-dependent dimensionless parameter. B squared, again, small v, you can see it as lambda QCD, but generalized. And large V is the generalization of the Vitagliano symmetry scale. Whereas N is, again, the number of walls attached to one string. And finally, this term produces a pressure PT associated with the tension of the wall. But these terms introduces a pressure associated, a volume pressure associated with the fact that different vacua have different energy. And when these terms, so the bias, gives a pressure which equals PT, you have annihilation of the wall. So it means that you can identify again another temperature, the temperature at which walls annihilate, which can be much, much smaller than all the other temperatures, because it depends on epsilon b, which can be small enough. Now, at this point, I can connect the dots and see what happens in terms of abundance of axions and abundance of gravitational waves produced with this mechanism. So there are three different mechanisms to produce axion-like particles. String decay, misalignment mechanism, and wall annihilation. So let's go through them very briefly. So for the misalignment mechanism, this is basically very, very similar to the case of the axion case. It's basically the same. So you have a certain energy density in the zero mode, which is 1/2 ma squared a squared. So this means that A simply theta misalignment angle times the U1 symmetry scale. And including the redshift, which is pretty obvious, so assuming entropy conservation, eventually you get a certain energy density stored in axions produced by the misalignment angle. So given that we are talking about the post-inflationary scenario, this means that you have to average over theta w squared, which gives you p squared over 3. So notice that this is fixed. It's a fixed number if you fix in the QCD axion case, because basically V is inversely proportional to M, so you just need to know the mass. And the other condition is coming from the fact that you want QCD axion to be that mass. In the case of the Axion-like particle, instead you have an additional freedom. Notice this number, which is order 10 to the minus 19, which will be important in a second. Because now we're going to talk about the axion-like particles produced by strings. So if you write down again the energy density stored in the string, which is mu over t squared times xc in the string network, sorry, you can use some analytical argument to predict what's the density stored in axions produced by string decay. And you see that this number is smaller than the other one. It's 10 to the minus 23, not 10 to the minus 19. But there is this logarithmic enhancement. So if this is large enough, string decay can contribute to the axion abundance. Again, there are people discussing about the presence of this logarithmic enhancement, while the contribution to axion-like particles coming from wall decay is much larger, because basically walls, all the energy stored in walls go into basically non-relativistic axions. So this means that if you write down the energy density stored in walls, it's simply equal to the number density of axions that get produced when they annihilate and the mass of the axion. If, again, you shift it to today, given that the annihilation temperature is not that large, the contribution coming from walls will be larger than anything else, because you see that this number is like 10 to the minus 24, and then there is this epsilon b downstairs, which is basically which measures how large the bias is. And the bias can be naturally small, let's say. So it means that if epsilon b is small enough, the contribution to the axion population coming from walls is dominant compared to the mesonomic mechanism contribution and the string decay contribution. So there are two take-home messages here. String decay can be more important than the mesonomic mechanism, subject to simulation uncertainties and also to the radical argument, as I learned recently. And wall annihilation also gives most of the contribution to ALPs for small enough epsilon b, because wall decay later, and it means that the contribution is less reddish.
But also, like this contributions, existence of string and wall, that's very model dependent, right? Because
Yes,
you
yes,
have
yes.
some specific UV completion.
Absolutely do, absolutely. It depends on the UV condition. Yeah, sure. So,
A question?
yeah, sure.
Well, I mean, the key players here are domain walls and strings, but nevertheless, you describe them in terms of some scalar field theory. It looks to me that it's more appropriate to write down a theory of strings, like a soup of strings, including breaking of strings and combining them to long strings. And this is the framework that you should solve to see what is the structure that comes out. And rather than this potential of a scalar field, which maybe, it's a special case of
Yeah, sure. But like what I'm doing here is simply like generalizing, what they are saying is correct. So what one can do is describing the soup of strings and describing the evolution of it. What people have been doing is like trying also with simulations to describe the evolution of the string network. With walls is somewhat is more simple, because like what I'm doing here is very similar to what people have been done in the 70s with domain walls, not attached to strings, but simple domain walls. And in that case, again, this is a toy model, and as you are pointing out, actually like real simulation and following the evolution of the network or finding an analytical argument for the evolution of the network might give different results. But again, this is the first step. I will let you know in the forthcoming future if these predictions are completely off. But my understanding of the topic is that they should be kind of correct. Now, for gravitational waves, of course, mesonomic mechanism, we can forget about it. So there are two mechanisms to produce gravitational waves in the post-inflationary scenario for Axionlike particles. One is from the oscillation of strings, and one is from annihilation of walls. Now, let's discuss about walls first, and then we'll see why string contribution is subdominant. So wall annihilation gives a spectrum which is like F cube at low frequencies, because this is simply coming from causality. From a causality argument, the gravitational wave spectrum at low frequencies in a radiation dominated era just goes like F cube. Whereas at a higher frequency, above the peak associated with the annihilation of the wall, this will go like F to the minus 1. And this is coming from some simulations that people have been doing for QCD axion string wall networks. I won't take it for granted. Like, let's assume that this is correct, but like I'm not 100% sure about this. Let's assume that this is true, and our axion-like particle mimics the QCD axion case for high frequencies. It's not important. What we need to know is that this is kind of peaked spectrum. So we will assume that it's a peak spectrum, which means that the power emitted can be written simply as like using the quadrupole formula, and by simply using basically. This is a very simple argument. We simply find that the power emitted in gravitational waves just goes like sigma squared beta t over t. So in a Hubble volume, basically, this will just be g sigma squared. Then we have to redshift it to the fourth because it's radiation, obviously. And you're left with a certain amplitude gravitational waves emitted by the annihilation of walls. This is the amplitude, whereas the peak frequency is obtained by simply redshifting Hubble. So given that basically the annihilate and the peak in the gravitational wave spectrum will correspond to Hubble at the moment of annihilation. So you see that it goes more or less at 10 to the minus 7 hertz times t annihilation over GeV. Now, if you assume, just for the time being, a certain f sigma over n. So f sigma, remember that it's a model dependent dimensionless parameter equal to 1, just you know, assuming some numbers. A T annihilation which is small enough, but not too small, because you want to produce dark matter before matter addition equality, obviously. And the amplitude can be 10 to the minus 12. This means that this spectrum will fall into the region explored by futuristic CMB experiments. But of course, if the amplitude is larger, this is already being these errors already been excluded by Planck. And indeed, if let's open a parenthesis about the strings. Why can we forget about strings now? It's that if you want to show what's so there are people who did the simulations of the gravitational wave contribution coming from strings, and I just wrote down a semi-analytical fit, which is this one, and you see very easily, this is 10 to the minus 15, you see very easily that for Pechenko symmetry breaking scale, so a U1 symmetry breaking scale smaller than 10 to the 14 GeV, you don't see anything. So even a U1 symmetry breaking scale smaller than like 10 to the 13 GeV, it's impossible to see gravitational waves. So the only way in which you can see gravitational waves from strings is if the U1 symmetry breaking scale is particularly large, and moreover, it's very difficult to have dark matter candidate in this case. So this means that.
Can you go back just 2 slides for the annihilation?
Yeah.
So if here. Next.
This one. Okay.
So at when the temperature of the universe is 5 electron volts, you produce both gravitational waves and
dark matter.
axions.
Yes.
But won't you get? I mean, and the axions will be semi-relativistic.
No, not really. Like it's
Well,
yeah, no, I
but
understand.
if they're not dark matter at that time,
No,
don't
no,
you
but
have
it's
issues with structure formation.
It's basically almost non-relativistic. So from 5 electron volt to let's say 0.75 electron volt, you can forget about the momentum of the produced axions, because Waltz annihilation produces almost non-relativistic axions, and how non-relativistic they are depend on simulation. So you cannot really tell if you don't do real simulations of it.
But even if they're not relativistic, I thought structures probing things. Well,
At 5 electron volt?
yeah, at 1 keV.
How?
With a small scale, we see structure enter the horizon when the photons are 3 keV. Just a matter of power spectrum. What's the matter of power
Because
spectrum?
yes.
it will behave like warm dark matter, right?
Yeah.
It will warm wash out small scale structure.
Yeah.
But then this should be an additional bound here, right?
But these bounds are gravitational waves.
Yeah.
We're talking about dark matter.
Yeah, exactly. But then it means that there should be a bound. So at keV. So the power spectrum at keV photon, like that's high redshift. No, I didn't think about it. Can we discuss it about it later? Because like I didn't think about this. Okay. Let's assume that I thought about it. And so this is what happens. Translating the bounds that I showed previously in terms of amplitude against frequency by showing on one axis the bias, and on the other axis the value of the U1 symmetry breaking scale. And you see that this corresponds to overclosure. This corresponds to the CMB Planck bounds, and this could be what can be explored by future CMB probes. So it means that there is a certain region which has already been explored by Planck, and the region which could be explored in the future, assuming a 10 to the minus 6 electron volt axion mass. Now, if you change the value of the axion mass, this plot will just scale and move along this line until you reach very small axion masses, which is 10 to the minus 14 GeV. And you see that here you need to take care of the fact that also strings contribute to the axion population. So this is coming from overclosure bounds if you account for the string contribution to axions, because such small axion mass correspond to rather high D1 symmetry breaking scale. Now this means that let's translate it to a popular Axion-like particle plot in which one shows usually, for example, the photon coupling, which we are not using obviously, but just to understand where we are sitting compared to other probes. we see that depending on the value of the bias, if the bias is in a 3-4 order of magnitude, plus minus this value corresponding to the dashed line here, no matter what's the coupling of the photons, you can probe axion-like particles, for example, down here. If you are lucky enough that the bias corresponds to something that can be observed so to low temperature wall annihilation, but like perhaps I was wrong. And the range of axions that can be probed this way, of axion-like particles that can be probed this way, corresponds to, given that we want that wall contribution to gravitational waves is larger than one from strings, because otherwise we can rely on higher frequency detections. You need the axion mass to be larger than around 10 to the minus 16 electron volt. And given that you want self-consistently that the single Bragg scale that gives axion mass is smaller than 10 to the minus 2 times the U1 single Bragg scale, then you need the axion mass to be smaller than, let's say, around 1 MeV. So this is the range that I'm showing here. So in conclusion, the presence of axion-like particle leads to the formation of topological defects, so cosmic strings and domain walls. For n larger than 1, domain walls produce most of axion-like particles that matter and possibly gravitational waves. And there is a window, depending on the value of the bias, in which the gravitational wave background from domain walls would be observable with cosmological and astronomical data, even if astrometry is not that good for the moment. And that's it. Thank you.
I wanted to ask about this, the value of the bias parameter. Like, is it easy to get it down to like 10 to the minus 12? Or?
Well, usually when people talk about the bias value, they claim that this might come from Planck suppressed operators. So it's not very small because you are comparing the value of small scales, like for example, the U1 single Bragg scale can be small enough compared to the Planck scale. And so the result is that if the operator goes like let's say b over m Planck squared, it's already enough to give you like numbers like 10 to the minus t squared, something like this. Which is why, for example, for the QCD axion, people have biases down to 10 to the minus 50. Otherwise, like, you know. But in the case of the QCD axion, the point is that gravitational waves are unobservable because the wall annihilation must happen much earlier. And so it means that basically you cannot get amplitude in gravitational waves larger than 10 to the minus 21. So it's something that it's unobservable.
If the bias can be that small naturally, is it not unreasonable then to think that, you know, in some model space sense, that the fact that you don't see in print that lambda CDM seems to work well already is placing limits on this. They could just as easily have been decaying at you know, redshift of 300. Is that reasonable to think?
No, it depends because like then you need to take care of the possible bounds coming from anisotropies because you have walls surviving.
Oh yeah, I don't mean from a bound point of view. I just mean from sort of like as I'm thinking about the universe and kind of what I would have expected.
Yeah, no, conceptual, yes.
That there could be, from a model point of view, there could be walls around right now. I mean, not experimentally, but
exactly, yes.
So really, bias could just be anything like.
Yeah, no, but that's why there are people like talking about, for example, direct detection of domain walls with like, you know, experiments like interferometers now, because like if you assume if you avoid the other bounds, so if you assume that you are safe from other bounds, there could be domain walls around now. So, yeah. Yes.
Yeah, so I'm still confused why you're playing the domain will produce most of the axion-like particles, because it seems to depend on the bias parameter. So if you turn on the bias parameter, then we're still go back to misalignment dark.
Of course, yes. So this depends. And that's why I should like plots like this one, because you see that if the bias is large enough, then you see that there is nothing to be tested because like it's safe, but it cannot be tested. So you need epsilon b to be small enough, so the walls need to be around for long enough so that, you know, they survive.
So you point out a region that walls will dominate.
Yeah, exactly.
So and also I have another question is why you say the log term of the cosmic string can be like 10 to the some power, because since log term is, for me, just naively think log terms very hard to be.
Yeah, but because the time that that strings are around is very long, because you produce them when there is the U1 similar Brigade scale, and then they keep on oscillating and producing axion all the way down to order m equal to h.
So it's just a time accumulation.
So it can be like 10 to the 3, 10 to the 4, because it's logarithm of a very long time, so over the mass.
Okay, thank you.
How do you see that domain wall annihilation gives you non-relativistic axions?
That's coming from simulations. I don't know if there is any argument, but I think that the only scale that you have is the thickness of the wall, and the thickness of the wall is order 1 over m.
But you can do it as a 1D problem, right? The
Yeah,
two,
exactly. Yeah.
two kinks approaching each other.
Yeah, no, I didn't do that. Yeah. There must be some argument around for it. I did I didn't check it yet, but given that I saw that from simulations it was order 1 of the mass, more like 0.5.
Any other questions for Eduardo? Well, thank you.
Thank you so much.
Lunch, yes. Dinner, she's not. I see. Yeah, I'm not sure